right, so just looking at 13A and coming back to those few little nuggets at the beginning that we hadn't covered because I wanted to make cranial nerves a priority in class. I am on slide 6, and just a reminder that sensation or detection of a stimulus isn't the same thing as perception. Our sensory receptors don't participate in perception. They only sense or detect a stimulus. So, and different sensory receptors obviously are sensitive to different stimuli. So, for instance, if we apply light or a change in light to a thermoreceptor, that thermoreceptor isn't going to fire. It's not going to launch an action potential because it's not sensitive to light changes. Also, whatever stimulus is appropriate for that particular receptor, it has to be applied within the receptive field for that sensory receptor. For instance, if we want to stimulate a touch receptor in the skin overlying the knee and expect to do so by touching the shoulder, honey, that's not going to work. Also, the density and connectivity of the neurons for those sensory receptors in that region has quite the influence. So let's look at slide 7, which kind of lays out that idea. When we're encountering a region, for instance, of skin that's less sensitive, there will be many sensory neurons that converge on the same, second order neuron, for instance, or converge on the same first order neuron. They're converging on the same neuron in a chain. Okay? And because they're sharing that neuron, if we apply two stimuli that match those sensor receptors in that particularly undersensitive field or receptive field, then the central nervous system will perceive the stimulus as just one stimulus, even though it's been applied actually at different locations. Okay, and if you think about it, sort of writing just one pathway because of that convergence, that might help. Okay, and classically, the way that this is illustrated is with the 2-point discrimination test, which you're probably familiar with already from probably having tackled exercise 23, but it does come up in exercise 23 if you haven't completed that yet, where the stimuli are 2 points, like 2 pins or 2 sharp pencils that are just gently but significantly poking the skin. If we're in a less sensitive region, then those 2 points, for instance, the 2 points of a compass, will be perceived as a single point, even though we're applying 2 stimuli. The brain is only, for lack of a better word, aware of one. Whereas in more sensitive regions, fewer of the neurons are going to converge. That fewer of the neurons are going to share their linkages. Okay, and therefore each stimulus in this particular scenario, each point of the compass or of the pencils or the pins or whatever, are activating their own separate, isolated receptive fields, and therefore the central nervous system perceives the stimuli as distinct. Moving on to slide This looks weird. I don't know what these red lines were originally. I think they were crossing things out. I'll be right back. Anywho, what I had crossed out, I don't need you to be able to recognize the phrase phasic receptor. And I don't need you to be able to define necessarily, at least not necessarily in those terms. When along the application of the stimulus, the receptor is active. Anywho, different, we're again on slide 8, different sensory receptors have different adaptability superpowers. So their sensitivity to a stimulus can potentially, depending on the receptor, change, be altered if the stimulus is especially lasting, like ongoing. And some receptors, we want them to be very continuously sensitive to stimuli because we don't want to be able to lose that sensation. We don't want them to adapt. For instance, we don't want nociceptors to adapt. Even though that would probably be our very first wish if we were being tortured, it's important that we know when the body is in pain. It's important that we have that sort of red flag, okay? Whereas touch receptors, the olfactory receptors, they sort of acclimate, they adapt. And therefore, the longer the stimulus is applied, the less sensitive they become. So olfactory receptors, touch receptors, they tend to be fast adapting. Nociceptors and most proprioceptors tend to be slow to adapt, or they simply don't adapt. Okay. I'm on slide 9, which we're skipping. I'm on slide 10, which we're skipping. I'm on slide 11, which we're skipping. I'm on slide 12. And on slide 12, we're skipping the first chunk, but we do need to know what referred pain is. And referred pain occurs when we perceive pain that's coming from one place as actually coming from a different place. And one of the reasons why that occurs is that the pain pathways from both somatic and visceral receptors often share the same nerves, and the brain therefore sort of makes assumptions about that pain sort of being applied to all of those relevant regions. For instance, you've probably heard before that you may feel left arm pain or left arm numbness during a heart attack. By the way, that is more common or more predictable in males than it is in females. Females tend to present a greater variety of symptoms during a heart attack, which makes them a little bit more difficult to diagnose. Scary. Now, this next slide, slide 13, is kind of just showing us a likely map of referred pain. So how to interpret this? For instance, let's say that our pain receptors in and surrounding the liver are being stimulated, okay? There's some pain-causing stimulus that's causing pain in our liver. We might feel that pain in the general region of the liver, but also creeping up a little bit on the same side as the liver. The liver's on your right side, into the thoracic region, and even into like the upper shoulder and lower neck. Okay, so in other words, the referred pain from liver pain, it can be felt in two relatively distinct regions. Just to make sure that you can interpret this particular image, excuse me, nice way for me to sort of ask about this image is to show you the image with the labels and ask you, for instance, which regions of the body, which viscera actually generate the most widespread, or can generate the most widespread referred pain, and therefore can be difficult to diagnose. And hopefully the answer to that one is obvious. The kidneys. The kidneys, right? Wow, that's really widespread, okay? Whereas stomach pain, pancreas pain, pain in the ovaries, urinary bladder pain, gallbladder pain, mostly isolated, with in the case of the gallbladder, the exception of including the shoulder. Isn't that weird? That's so weird. Anyway, referred pain. I'm on slide 14, which we're skipping this quarter, and I'm now on slide 15. So when we were studying skeletal muscle way back in chapter, good grief, I want to say 9. Does that sound right? I think it's 9. We found out that skeletal muscles have subunits that are called fascicles, and those fascicles have subunits that are called fibers, and those fibers have subunits that are called myofibrils. Is hopefully ringing a bell. Well, the structure of a nerve is actually really, really similar. Really, really similar, okay? Because sure enough, connective tissue sheaths, okay? We already know that there are two really general, broad types or regions of nerves, the spinal nerves and the cranial nerves, really just depending on where they emerge from the skeleton, okay? Moving on to slide 16, here's the layout for the structure of a nerve. Once again, notice connective tissue sheath. The outermost one is called the epi. Outermost is often epinurium, okay? And each epinurium houses a nerve, a single nerve, okay? But the nerve has subunits, which are, this might please you or alarm you, they're called fascicles, okay? Each fascicle has a connective tissue sheath around it, which is called a perinurium, okay? And then each neuron within a fascicle will have another connective tissue sheath around it called an endoneurium, which is not the same thing as a myelin sheath. The myelin sheath does not have to be present. Oh, good grief, that looks horrible. Anyway, so epinurium, perinurium, endoneurium, in that order from superficial to deep, okay? And then the next, well, really the rest of the chapter, or not chapter, file 13A, it's cranial nerves, which we already did together.